This final video is going to involve multi-step synthesis problems based on alpha carbonyl substitution reactions. Okay, let's see. First problem at the top. What do we know about this one? Okay, we can see a few things about this. One, oxygen is probably here, so let's take advantage of the fact that we don't really have to move the oxygen if we just keep it in the same place, like where I've asterisked this. If that's the carbon that corresponds here, we don't need to move the oxygen to a new carbon. If we look at that, that's the alpha position. That corresponds to the alpha position here. So we know that while this compound is a ketone or any other type of C double bond O, we can easily substitute the alpha position. Okay, some other things to note: even though the oxygen's in the right place, it's not at the right oxidation level. There's going to have to be a reduction. However, we can't reduce it right away because that means the alpha position can't be substituted anymore. The way we think about these problems should be in a retrosynthetic way, working backwards, and we'll do that here. Sometimes when the problems are relatively simple, you don't really have to do that, but we'll stick to the better plan this time as well. Okay, all right, so what would be a good last step? All right, we know how to reduce ketones to alcohols, but we don't know how to reduce them to ethers, so that's probably what we want to think about first, putting in the ether. All right, so the last step is going to be make the ether. And what we would want to do is the Williamson ether synthesis on the alcohol, right? Okay, so the immediate second to last compound in the synthesis would be this alcohol right here. We see something that's directly producible from a ketone by a simple reduction reaction. Okay, so our likely next to the last product would be the ketone right there. And you can sort of see that if we look at the relationship we have between this compound and this compound, that looks really just to be an aldol condensation product. So let's do the alpha beta business. Remember that in the aldol, that we'll analyze the alpha beta unsaturated this ketone this way. The alpha position corresponds to the deprotonation site, and the beta corresponds to the C double bond O of the, I'm not really clear if I got this donor acceptor business right here, but the other partner, the beta carbon, is going to correspond to the C double bond O of the other partner. Okay, so all we would need here now is benzaldehyde and base. Okay, we'll just say KOH ethanol reflux. All right, so we'd have a three-step synthesis. This would accomplish this very nicely. Let me just say, I've taught organic chemistry many times, and what are some of the common wrong answers? The most common wrong answer is that people will do a Wittig reaction in the first step, okay? That's not really the thing we want to do here because that really destroys the oxygen. We need to reinstall it later. Let's take advantage of the fact that we already have it. Okay, let's do the next one down here. This is interesting in that if we actually did it, of course, you could get in serious trouble, but you probably would have a hard time getting the precursor compound too. That's also a controlled substance. But let's look at some relationships between the product cocaine and the starting material tropinone right here. Okay, again, we have the oxygen here at the same corresponding to the correct place in the product. This is something added to the alpha position. Okay, so there's the alpha position there. So that's easily done by some sort of condensation reaction. So let's take advantage of all of these things. We have the oxygen in the right place, but it's not at the right oxidation level. A similar analysis we're going to do with the one above it. We know how we can turn ketones, we can reduce ketones, but ketones reduce to alcohols, not to esters like this one. So let's make the ester in the final step. Okay, so in the second to last step, let's just take the alcohol and turn it into the ester. The mildest way to do that is by the acid chloride and pyridine. We already have an amine in the molecule, but that's not going to interfere because it happens to be a tertiary amine, and we cannot make amides from tertiary amines. There's no active hydrogen on nitrogen, so that's not an issue right there. So that's a good second to last step. Okay, ketones are more reactive to reducing agents than esters are, and we also have the can take advantage of the differential reactivity of these two reagents. Sodium borohydride reduces ketones and aldehydes, whereas lithium aluminum hydride reduces all C double bond O compounds in some way or another. Okay, so what we would want to do is just use the selective reducing agent, sodium borohydride. Apply it to this compound. We have a ketone and an ester. It's only going to reduce the ketone. As far as the stereochemistry goes, it's not totally clear that I'm going to get the right stereochemistry, but one of the things that's probably helping out here is the fact that right here is a 6-membered ring. So what's the conformation like? If it's a chair, it would be like this, right? So this would definitely be the less hindered side. Okay, all right, so that would do that. And now we can do a reaction that we've done previously. We need to need to add that to the alpha position. This is a reaction again like the Claisen condensation, right? So what we're going to do here is we're going to treat this with sodium methoxide methyl carbonate, and then acidify, and that should produce that compound right there. There's two alpha positions, but this is a symmetrical molecule, so it does not matter which alpha position is attacked. So this would be a three-step synthesis that would accomplish the objective that you see there. Okay, let's look at this one. This top one is a classic example of the acetoacetic ester synthesis, and the one that's related to it, the malonic ester synthesis. Okay, now one of the things that people get wrong about the acetoacetic ester synthesis is that all the other reactions in organic chemistry have been concerned with making the molecule bigger one step at a time. In the acetoacetic ester synthesis, it's inevitable that this group here will be lost in a ester hydrolysis decarboxylation sequence. But we need that group there to enhance the acidity of position 3 so that we can do the very easy alkylation reactions. This one I'm going to do in a forward synthesis because you can see that we basically just added an allyl group and an ethyl group to position 3. And this is a fairly simple operation. Okay. We'll call this step 1. Step 1 is going to put an ethyl group at the alpha position. Okay, okay, in step 2, it's going to put the allyl group in. That gives us this compound right here. Okay, we'll call this step 2. A person trying this would, of course, probably try it both ways and see which way works better. Generally, it's better to put the more reactive SN2 substrate, which is an allylic substrate, in second. Okay, that usually works a little better because it's a little harder to do the second SN2 reaction since it's more hindered. But in theory, it could work either way. All right, once this is in place, we're going to hydrolyze the ester. Get the acid. And then we're going to decarboxylate by heating the system like you see here. It is possible to go straight here with a acid catalyzed route. Okay, you can decarboxylate the carboxylic acid, but you can't carboxylate the carboxylate anion. Okay, so generally the base catalyzed ester hydrolysis is more efficient than the acid catalyzed ester hydrolysis, and it's usually the preferred way to go. But if In theory, the acid catalyzed route would have the advantage that you could do that step simultaneously with the decarboxylation. All right, what do people mess up here? The biggest thing I've seen people mess up on is they try to turn the COOET group either into an allyl group or an ethyl group because they don't have the concept that the carbons are lost. Okay, so this is one where we lose carbons. You have to sort of change your way of thinking in that respect, but that's something that you have to understand, that it's there as an activating group. It's there to enhance the acidity of the hydrogens at carbon 3. Other mistakes people make is decarboxylating and then adding in the allyl groups. That's going to give you a selectivity problem in step 2. Okay, you're going to have an unsymmetrical ketone that you have to selectively alkylate on one side or the other. So it's much better to keep the ester group in place until the very end. All right, this one here, the second one is an example of something called the malonic ester synthesis. The malonic ester synthesis typically produces carboxylic acid. Okay, this is a 2. All right, sorry, should have been erased. Okay. All right, so what we're doing is we're adding groups to the alpha position of a carboxylic acid here. We don't have a carboxylic acid, we have an alcohol, but we note here that lithium aluminum hydride followed by an acidic workup of some sort could do the job there. Sorry, let me keep it the same. Yeah. All right. So that would would allow us to take that direct result of the malonic ester synthesis and turn it into the alcohol. So let's have that as our final step. Okay. And so you'll see if we think of this now as being carbon 2, we see what we've added to it is a methyl group and a phenethyl group. Okay. All right, so all we have to do if we want to apply the malonic ester synthesis is just add a methyl group and a phenethyl group to carbon 2 in a series of alkylation reactions. Okay. All right, so let's go ahead and do that. Step 1, we'll add the less reactive group, 1-NaOET. Okay, so do the alkylation. And that should give us this. In step 2, we'll add methyl. Methyl's the more reactive halide, so it probably give us a better yield if we add the more reactive one second. Okay, being the better SN2 substrate, but in theory, it's okay. to reverse steps 1 and 2. Okay, now we have to apply the malonic ester synthesis, which is exactly like the last 2 steps of the acetoacetic ester synthesis. We're going to hydrolyze the esters and then perform a decarboxylation reaction. Okay, all right, so NaOH, then acidify. It's going to turn both esters into carboxylic acids and heat it to greater than 150 degrees C. You'll lose CO2. Decarboxylation is going to produce that product there, which we've identified as the second to last compound in our synthesis. Okay, again, mistakes people make are trying to turn one of the COETs into one of the alkyl groups there. It's important to remember that in the malonic ester synthesis, one of these groups we have to regard as just being temporarily there to enhance the acidity of the hydrogens at carbon 2, so we can use the weaker base sodium ethoxide and sort of direct very efficiently the deprotonation reactions to that site. Okay? All right, so that would be how we would make this. I have one more problem. This is, if you're in my class, this isn't on your problem set. It's actually in the lecture, but I just want to put it here. This is a common type of problem called a roadmap problem. I don't have the products here pictured. We're going to have to go through the synthesis and figure out what G and H are based on our ideas of the reactions here. All right, so if we look at these reactions here, the first reaction is an epoxide reacting with a Grignard reagent. This is just a nucleophilic ring opening. We know that it produces this compound, probably with the definitely with the trans stereochemistry because of the constraints of the SN2 reaction, but we're not really going to worry about that here because the relative stereochemistry, we're going to get rid of it in the next step. Okay, so PCC is of course for alcohol oxidation. We're not going to worry about the aldehyde versus carboxylic acid issue since this is a secondary alcohol. Only the ketone can be produced. I'm going to not draw the stereochemical wedge here anymore because in step A we also produce the enantiomer in equal amounts. Recognize that neither starting material is chiral. Methyl magnesium iodide is not chiral. The epoxide's not chiral, it's meso, so we could, even though it's making a chiral compound, it would make it racemic, so we're just going to leave the methyl not touched there, okay? Or we're going to leave the methyl without any sort of stereochemical definition, okay? Here, we're going to add ethyl to the C double bond O and get the alcohol. There's probably some stereochemical control, but we're not going to worry about it because this is another one where we're going to get rid of the stereochemistry in the next step. Okay, so I'm supposed to write it here. Okay, hope I don't have a picky grader that would take points off for that. Okay. Actually, most organic chemists wouldn't. I wouldn't, but I do like it to be neat. I like every person to put it in exactly the same place for assembly line grading. Okay, this is a dehydration. Okay, we want to produce the most substituted alkene that we can produce. And there is one tetrasubstituted alkene that we can produce. And that's this one. So this would very likely be the product right there. Okay, and now we're going to cleave the double bond in step D. So step D is an ozonolysis, or using the osmium alternative. Either one turns the C double bond C into two equivalent C double bond O's, and there's no direct bond between those carbons anymore. Okay? Okay, this gives us a product that has two carbonyl groups in it. Okay, and if you now look at the reactions that these can do with base, this would of course be the intramolecular aldol condensation. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, we have 8. We don't want to do 4-membered ring aldols, so so if we look at all the alpha carbons that have hydrogens, there's a lot of them, but we're not going to consider these two. Deprotonation here. Will afford 4-membered rings eventually, okay? If I take either those asterisks that I put in square and draw the arrow, make the bond to the C double bond O, the ring size I'll get will be 4, and I don't want that, okay? All right, so let's only consider 6-membered rings. All right, so we have aldol A and aldol B, okay? Again, these are not reaction arrows, these are what goes where arrows for the aldol condensation, okay? So we're going to remove the two alpha protons eventually and make a new CC double bond, okay? That's what happens in the aldol condensation. There are many previous examples of mechanistic discussions of that process. Okay, so let's look at A. A is going to okay, so aldol A, aldol product A is that. Aldol product B is this product right here. And let's see which one matches the NMR spectrum better. Okay. It's actually pretty easy to identify these, okay? This one has an alkene hydrogen. An alkene hydrogen ought to come 4.5 to 6.5 ppm, but that's not present in the NMR at all. The NMR, its highest chemical Schiff peak is at 2.6, so there cannot be an alkene with a hydrogen on an alkene carbon in the final product. So it's not A, it's B. All right, so B is the final product. I guess I should call them G and H. Sorry, G and H. All right, so we're going to say that that is H there, and H is the product. Okay. Obviously, how a person would label whether you would choose that the one on the left is G or the one on the right is G. I don't know. That's not important. What's important is that you recognize that the final product is the one that has a tetrasubstituted alkene and thus no hydrogens directly on the alkene. Is this consistent? Okay, we have a triplet at 2.6. Okay, that would be that, right? 2.6 right there. A triplet at 2.4. 2 hydrogens, 2.4 right there. A singlet for 3 hydrogens and another singlet for 3 hydrogens. We'll say that this one being closer to the C double bond O is 2.0. This one 1.8, but that chemical shift is too close to really make that a reliable assignment. And finally a quintet. I think this is a typo, sorry, at 1.6. Right there. Okay, so yeah, 1.6 parts per million right there. Okay, anyway, I hope these video problem sets have been helpful. Hopefully you don't need me, okay? Need my narration. Hopefully you can do it on your own, but this should provide helpful hints to get you started. If you don't see it right away, you can, again, it's best to start trying this on your own and then start playing the video as you need help to finish it. Okay? All right, so that ends this series here. This is the last in the series. I don't have any more on the carbonyl alpha substitution part of this class.